Hello guys, welcome to this new video. In this video I will be explaining you how to do a load analysis on a random surface. And first of all I will be making this surface using Grasshopper, and I'm going to create multiple points, symmetrical points on this surface, and I am going to make a line using these points, and these point will act as a joint for these lines, and the lines will be converted into beams. So what you will get in the output is a complete surface structure with beams uh, and joints connection, and in the end you can see here at the bottom these are supported joints in XYZ direction. So these joints are only at the bottom of this surface to support this surface, and after that this structure will act as a truss system, and later you can apply forces on the joints of this truss system at different points, as you can see here, and you can select on which points you want to apply the forces. So this is what we are going to achieve in our Grasshopper session. So hope you guys enjoy this tutorial. Okay, let's start with the first step. We have to create a curve, and now in this curve function I will set the curve as this one on the right side. Okay, now as you can see here, one locally defined value. Okay, the value has been taken by the function. Now the next step would be to make the mirror of this geometry, so it automatically takes the YZ plane, so no need to separately add YZ plane on this mirror function. Now the next part will be dividing this curve. So I have actually two of these curves. One is this one and one is this one. So I require the divide curve twice. So I right click, Alt, copy it, and connect one of the curve here and the second curve here. So right now the count is 10 by default, but I want to change this count as per my requirement. So I'll create a number slider of 25, and I connect this count here, shift add, shift add. So you can see here these curves are divided into 25 parts. So now in the next step what I will be doing is creating lines from these points. So I want to create a line from this end to the opposite end. So for that I will create a line function, not this one. Yeah, this one, and I will put all these points from here to this side. So you can see now these points are created, sorry, these lines are created from these points. So now in the next step what we will be doing is we will be evaluating uh, this curves, because we want to create a vertical height, as we want to rotate this curve and make a surface. So we need a height so that we can create an arc from these 3 points, and then we can loft that surface. So I'll show you how we can do that. So for that, let's evaluate the curve and put the curve here, and Our parameter here will be, say, 0.5. So we get a point exactly at the center of the curve. So we got this point, and I want to move this point at, say, some height. I use this function, move function, and I will move this. So right now it's taking by default 10. So it has moved the point 10 units above, but I want to move this points with a specific height. So for that height, what I will do is I will take the length of this line. Okay, so I will use this command length where you get this length of the curve. So I will use this line and add it here in the curve. And the next thing I will be doing is a division to get a value of the approximate value, half value, so that I can move these points approximately to that value. So yeah, this is the division, and I put this length here, and I will also have a separate slider for dividing this factor, that is the b value. And yeah, as you can see now, I have this ready. So the result you can see here is different for the 26 values. So you can see the same curvature on the top as well because of this particular setup. Else what would have happened is it would be a straight line, but I want this same curvature on the top, so I do this. And now the next part, what I will be doing here is I will be using the unit Z so that I convert this result into a vector and feed it to this part. Now you can see I have formed similar type of curve on this Z plane. So yeah, so that was the reason why I did this. And now the next part will be creating a arc. So for creating an arc, use the arc command. Now here we require actually 3 points, but as you can see, this is not a 3-point arc command, and I will be using a 3-point arc command. So here we have options for 3 points, and I will use uh, these points, this point and this point. So for the first set of points will be from this, second set of points will be from here, and third set of points will be from here. Okay, so now you can see this arc created on this points. And okay, and the next step now here will be we are going to loft these arcs so that we create a surface. So I put all these curves here. Now we have created our surface, required surface. So we are done with the first step of our design here. So let me quickly scribble this and mention it as first creating surface. So this was the first method, how to create the surface. So I'll select all of them, and group them together. Okay, so this was the first part, and now in the second part what I will be doing is I have to create panelings for the second part. So basically this arcs created a surface, but now I want to divide this entire surface into small panels so that I can use that edges from those panels to create beams and points as supports. So for that I will be doing a paneling. So how I would start the paneling is I will use a subsurface function that is basically isotrim. Here you can go in the utilities and find this option isotrim and put all the surfaces in here, and now divide no domain. So yeah, I want to divide this domain into number of panels. So for that I need the domain, that is the loft surface itself. So now you can see here it has divided the surface into panels, but it has taken the u and v value as 10, but I want to divide it as per my requirements. So I will actually put this u value in the divide curve. So I want to keep symmetric to this point, so I will put it here. You can see now these lines are exactly divided from here, and the next value I will create it here. I would also put it as 25. Okay, so now I will connect this to V, and now you can see there are 25 panels here on one side and 25 panels on the other side. So that's how we do paneling for this surface. And now the further part would be we have to use the points of these panels, that is the uh, vertices of these panel and the edges for creating beam functions. So I will be deconstructing uh, this planes. So basically these surfaces, so I put this surface in the prep, and now you can see here it divided it into a lot of vertices edges on the right side. So yeah, so let's get to the next step here. So in the next step what we'll be doing is indexing of these basically the vertices, not the edges. So I will use a number slider here to just put the index value for the indexing, and yeah, left click alt, and I create three different, not actually three, four. So I create four different list item, and now I connect all the vertices into this list. So now as you can see, if I select this, you can see a list of points getting selected in 0, and that's the same here. But when I change it to 1, you can see it has not selected the points below, but here also it has not selected points below, and the first uh, arc points are also not selected, but here you can see it's selected. And here we change it to 2, and you can see now this part is selected and this part is not. Here it's the opposite. Here it's this one, and here when I do it as 3, so yeah, you can see it's different here as well now. So all these parts are different from each other. And in the next part I will be creating a 4-point surface. Yeah, and I need 2 of the surface, because as I will be creating 2 triangular surfaces in one panel, so I will be connecting the first item with the first corner, and the second one with the second, and yeah, the third one with the third. And here I will do the same, but the first one will be this one, and the second one will be this, and third one will be this. Okay, so as you can see now, there are 2 triangles. You can see now this triangle and this one getting selected. So this triangle will help us to create a beam from this end to this end. So that's why I am creating this surface to make these beams, symmetric beams all over, and then we'll have a truss structure. So now the next part will be combining both of this surface together. Shift add. Okay, so now you can select all of them together, and the next part will be putting the data. Okay, so now I will be using deconstruction grep command here, and I will be adding these surfaces in this, and now you can see all these lines and points are deconstructed, and this data, these edges will be used further for making line to beam. And as you can see, we did paneling with all this setup, so I will scribble this part as uh, paneling. So paneling surfaces, paneling surface. So I create this here and group all of them. Okay, so we are done with the second part here now, and so now what we have here is this deconstruction grep data, uh, which can be used for making line to beams and also analyzing the surfaces. So let's first make the line to beams using these edges. So I will be using line to beam option, which is here in Karamba 3D, and I will be adding all the edges here, and I will identify them as beam. So okay, I identify them as beam, and Now what we have to do is we have to assemble these parts in the next step. So I will do the assemble model and put all the elements here. So this is our final setup to do a analysis on these beams. But before that, we have to select the points for support at the bottom, and yeah, so let's select the points for support at the bottom. So for that, what I require here is point deconstruct. So I will be taking these points from here. So as you can see now, these points will be simplified further using this smaller than function. So if the value of the z, that is the vertical height, so value of z is less than say 0.01, so all the points at the bottom are at 0, creating support. So all the bottom points will be acting as support for this surface. So for that I will be okay, so I will use the skull pattern command now, and I will use the smaller than as the cull pattern from the list of these points. So you can see now 150 points which are at the bottom. So as you can see here, we have divided uh, this number of panels into 150 points which are here. You can see, so these are points are all the points at the bottom, as you can see here, which has been selected, and now these points will act as support. But for that I have to first create a support command, and yeah, I will be clubbing the data here and renaming it as support, and we'll be adding all these values here and create a support in Karamba, and I will fix it from all the directions. And I'm going to add it in the assembly now. So to have a view of the support, we have to go further, analyze this model, and then model view. So now you can see all the supports have been fixed, and the next part what we have to add here is the loads, and uh, yeah, basically the loads on this surfaces, so especially on the beams. So what I will be doing for that is, okay, so there was a problem here. I have to disconnect it because you can see when I select all of them, it's selecting the points as well as the lines. So I will disconnect this, and I have to now make a line data. Lines, I will be adding this lines here. Let me flatten this so I don't have any copies of the lines or multiple lines. So I will put all this line into this, and now you can see these beams are now selected here. And now let's add the loads on this surfaces. So I will use the loads command in Karamba, and let's add gravity first, and let's copy this and use a different type of load. Now it will be a point load, and let add this load on this model. So for selecting these points where you want to put the load, we have to do something like this. What we did is we selected some points for creating the support. So I will scribble here creating supports, and let's add all of this into a group, and let's keep these loads above. This is our analyzing part. So now we need a set of points on which we can put these loads. So for that, let's take these points from these data. So what I will be doing is, okay, so now I will be using the prep join command here, and I will be taking this surface data from here, and I will be using these surfaces. I'll be using the curve prep command to solve the intersections of these curves. So I will put these prep here. So now the next part will be analyzing the direction of the line. So I will be using these points here. The direction what it has taken is the Z direction. I want to change it to the Y direction, and I will use this unit Y vector to change the direction of this line, and I will use the value of 100 as the length of this line. And you can see now these lines are created. In the next part, what we will be doing here after creating this lines is we will be using these lines in this curve to check the intersection overlaps on this curve, and these overlaps is what we require to compute to get a position for our loads. So now what I will be doing here is I will be creating a list length. So from this I will put all these points into this list length, and after that I will be evaluating it with this logic condition where I will put all this length numbers into the first number, and the second number will be this, and as you can see here now, so 676 values both of the side, and when I flatten this I get all the values are whether true or false. So I use this part now to check. So now what I've got are some points here which are smaller or equal to 1. So what I will be doing is I will be curl pattern. So I have these points as the list, and this is my curl pattern, and I will be using this part to just add the point loads here. So now I will be creating a force, say 10, and it will be in the Z unit direction, and yeah, and this direction will be reversed because I want it acting in the negative direction, so I can use this reverse vector function to reverse the force, and I put this force here uh, into this load, and now I add the load into the assembly model, and I press shift and add the gravity again. So now as you can see here, the assembly model I don't want to show this line direction, so I will hide this, and now you can see I can put loads on this truss structure, and then I can uh, okay, so as you can see now the force is acting on every point on the structure, so we have to manipulate this value as we require it. Maybe I keep it as 10, and let's check what happens at different value. So As you can see here, the value we are going to check for this list length, and you can see most of the values are 0. All the values are 0. So here now you can see after adding this load on this element, I can see my model where the loads are acting. So if I keep on changing this value for 1, 2 and 3, that is the second number, so it will then select uh, the points as per this data tree, where you can see different points with different values 1, 3, 2 and 4. And so if I do only 1, so it will compare with that value, and whichever value is equal to 1, it will apply force on this uh, point. So as you can see, what we did here is we took the breadth of this entire surface, and using the breadth curve, uh, we made the points and the curves. So here you can see the curve list is empty, but we have the point list, and here we took all these points, and if you want to see the points, you can use the point command and check which are these points. So you can see all these points got selected in the entire surface, and then what we did is we made a list of all these points, and for every list there's a value of the length, and as per this value it changed the number of loads acting on this surface. As you can see, if I keep on changing the value, the force distribution changes on the surface, and yeah, that's how you can manipulate the forces acting on this uh, surfaces. So yeah, and and you can also definitely apply forces if you want to apply it exactly on some points, or uniform load forces. You can do that as well. You just need to take the points and the curves and the edges from this data tree, and you can apply these forces in a manner like this, and you can use some conditioning like the smaller than condition here. Using this you can make like point forces, and I will scribble this and write it as uh, applying point forces, and then I will group all of this together, and now you understand how this conditioning works and how the list from the skull pattern list for these points, the positions are determined for these loads, and we apply a 10 unit force on the negative z direction. And you can see the assembly model here, you can analyze it. And now if you want to see the beam view, you can do that as well. So you can see the deformation, utilization, displacement of this geometry. So I will decrease the scale of this. As you can see, the cross section is really big for this. I would like to reduce it a bit. So let me check. In this value, it's taking, okay, the empty cross section parameter. Yeah, so this is the basic way how you can show your axial stress, and the cross section is here. Okay, so I can control the faces from this part, and yeah, I changed it to 1, and now you can see the axial stress and the utilization. Okay, so now in the next part, what we have to do is we need to put a gradient, and yeah, we need to change the type as maybe this one, and we need to set a range, and the range will be this parameter, and add it in this color, and just reverse this. So basically this is the lower limit, and this is the middle one, and this is the highest limit. And okay, so now in the next part I will create a legend where I will get the colors and the tags. Okay, so now you can see here I'm not able to get the colors and tags. That is because I didn't flatten the elements, support and loads. So I need to flatten the data tree for this element, support and loads, and then you can see the color ID here for different parameters. So you can see the utilization happening here, and uh, this is the displacement. At the red point you can see the displacement is really high. It's almost deformed from the shape to the other shape. So yeah, this is how you can do a truss structure load analysis on different supports and points. And yeah, this is the entire definition for making this this data for generating this output. So I will just zoom out this a little bit so that you can see it clearly. You can see this part of the structure. Yeah, so this is the final output we generated from the beam analysis for this structure. So just comment below whether you want the definition for uh, this solution. If I see there's a lot of response, if a lot of people are interested, I would like to share it as well. So thanks for watching this video. Again, I will go through all the parts so that you can even take a screenshot quickly of that. So I'll zoom in this part, first creating surface, then paneling the surface, then applying point forces, creating supports, and generating the final result. Okay, thanks for watching the video.